This video is going to discuss the first derivative test, which is a method of classifying local extrema, and from there we can also start to identify global extrema as well. Okay, so first derivative test, it's a procedure, and what it says is if we're given a differentiable function f, so we have to be able to find the derivative, and we have the critical point, so remember this is where f prime of c is equal to 0 or does not exist. Okay, so we've had to have already found those, but from there we can classify that critical point as a local minimum if f prime is negative to the left of that value and positive to the right. So what I like to do is I like to make sign charts for all of this stuff. I find it's a good way of organizing the data, and it also allows me to see this stuff visually too. But on a sign chart, think of it as a number line where you list your critical value, or the value at which your critical point occurs, and then I'm going to separate it into two parts. There's going to be f prime above, and it said it was a minimum if it was negative to the left. So in this region, it would be the derivative would be a negative value, and it would be positive to the right. Okay, and just so we know, to find this, you would need to find by using a test value. Okay, we'll see how this works in an example. Okay, but then similarly, if f prime is positive or negative, I can actually look at the derivative or the function itself. If the derivative is negative, that means that the function is decreasing. If the derivative is positive, that means the function is increasing. Okay, positive number goes up, means that, or positive number for the derivative means that the function value is going up. So that's where I get intervals of increase, decrease. And then of course at the critical value, for right now we're going to assume that the critical value is 0. And then so we can actually see sort of visually that we go down and hit the bottom of a hill. Okay. Local maximums are going to be quite similar, and so if I make a sign chart for this, for f and f prime, I actually see, okay, again, here's my critical number, f prime. I'm going to have positive to the left and negative to the right, and so looking at the function itself, that would go from increasing, this would be 0, this would be flat, and then this would be decreasing. So I get a sort of hill shape, the top of a hill. Okay, and so that's going to be when there's a local maximum. For a saddle point, which is the third type of critical point that we could classify it as, we're going to get a sign chart. Let's see, sign chart. There's going to be two different cases that we're going to have to deal with, f and f prime. Sign chart for f and f prime. I get critical numbers. And so we're going to either see for the function, or for the derivative of the function rather, positive and positive on either side, or we're going to see negative and negative on either side. And what this means for the function itself is that it's increasing, flattens out, and then in it is increasing. Here it would be decreasing, flattens, decreasing. Think of the cubic graph for something, for a quick example. Okay, so it would be increasing, here would be my critical point, and then it would be increasing on either side. So that's a saddle point. Okay, then the overall scheme for the first derivative test is, well, we need to determine the derivative, find the critical points, okay, determine the domain. This is going to be useful for us towards the end of the problem. Okay, so determine the domain, and also if there are any endpoints. Okay, and then with those critical points rather, you can start to classify them by sign charts. So this is exactly what we discussed on the first part of the video. So maximums, saddle points, and minimums. Okay, and then the other thing that we need to make sure that we account for, rather, is the endpoints. And this next procedure, this is typically called the closed interval method. Okay, and the closed interval method is the way in which we classify global extrema. So if f is increasing or decreasing into the endpoints, then we can start to make a list of function values of the critical points and endpoints. So this is essentially critical points and endpoints. Find all values, let's say a comma f of a. Okay, so this is going to be the x-coordinate of either the critical point or the endpoint and their corresponding function value. Okay, and then from this list of values, the largest is the global max, the smallest is the global min. Okay, there are more details in the course notes, and I encourage you to review those for a full description of this method. Okay, but we want to use this method to define and classify all extrema of f of x as defined here. Okay, so the first step was to find f prime. Okay, so f prime is equal to taking the derivative here, so it'd be 5 1/5, so this would be x to the fourth plus 2x cubed minus 3x squared. I'm going to rewrite this as x squared parentheses, just factoring out an x squared plus 2x minus 3. Okay, and from here I want to find critical points. So let's see, set this equal to 0 and solve. I'll let you work this out, but I end up getting 0 as the x-coordinate of 1 from this first part, and then it should be -3 and +1. Okay, then I actually need to plug these into the function to find their values. So 0 in for all the x's here, and I get out 3. Put in -3 and 21.9, 1 and 2.7. Okay, so I found my critical points, and then after that I want to find the domain. Well, luckily the domain's already done for me, and this is a polynomial function, so it's continuous on its domain. Okay, and then here, now I need to start to classify these critical points as either local mins, local maxes, or saddle points. So I'm going to, so 3 was done. 4, I want to make a sign chart. Okay, so it's a sign chart for f and f prime. I'm going to list my domain, so -4, and then my critical points are -3, and then let's see, 0, 1, and then the end here is 2. Okay, and I can't go past those because my domain's restricted. Okay, and now I need to find the sign of f prime in each of these intervals. So I'm going to say, let's take f prime of, say, -3.5 for this first interval. Okay, and then in here I'm going to say, oh, let's do f prime of -1, and f prime 0.5 for this interval, and then f prime of 1.5. Okay, so I actually have to take each of these values and substitute them into the derivative here. Okay, either form, doesn't much matter. Okay, for me, I'm just going to list out the sign that results. You should actually compute out the value. But f prime negative 3.5, this is going to be a positive and a positive, and then I actually need to do the computation. So, alright, and when the computation is done, it turns out that this is a positive region, so I would have to put in negative 3.5, evaluate it, get out a positive number. Here, put in negative 1, and I get out a negative number. And then put in 0.5, I get out a negative number. And then at 1.5, I put that in, I get out a positive number. Okay, so then in terms of f now, okay, just a reminder that if it's positive, that means the function's increasing. Here it's decreasing, decreasing, and then increasing. Okay, so now I think I have enough to classify a local extrema. Okay, so local extrema. Okay, so let's see, if it switches from increasing to decreasing, that's going to be a hill. So that is, or from positive to negative, by first derivative test, this tells me that I have a local max of 21.9 at x is equal to negative 3. At 0, it's decreasing and decreasing, so it's going to be a saddle point. Of 3 at x is equal to 0. And then this last one at 1, this is a local min of 2.7 at x is equal to 1. Okay. Then the next thing I need to do is classify global extrema. Okay, so I need to make a list, again, of all the coordinates of all my xy pairs of my critical points. So that's 0, 3, negative 3, 21.9, and 1, comma, 2.7, and endpoints. So this is crit points, endpoints. So endpoints were -4, and then if you evaluate it, you get -9.8. And then here you also get, let's see, 2 is the other endpoint, evaluated at 9.4. Okay. Now the largest of these, the largest y value, is going to be a global max. So the largest is here. This is going to be my global max. Okay, global max of 21.9 at x is equal to -3. And then the smallest is going to be the global min, which is right here at -4. So it'll be global min of -9.8 at x is equal to -4. Okay, and with that, I've classified the local and global extrema and completed this problem. Just to review what I did: found the derivative, set it equals 0 to find my critical points, which are right here. Then with my critical points, I made a sign chart with f and f prime. You don't technically need f, but it's often useful just so you can understand whether it's increasing or decreasing. Then, using the first derivative test procedures, I was able to classify -3 as a local max because it switched from positive to negative, the derivative did. And then 0 was a saddle point because the derivative was negative on both sides. At 1, when the derivative was negative to positive, so that was a minimum. And then global extrema, I had to find the x comma y pairs of my critical points and endpoints, classified those, or it took the largest as global max, smallest as a global min.